welcome back. So we had left the last lecture and we ended on flash memory drives. I told you that transistors with a floating gates are used in your flash memory drives. So transistors have wide applications, and we have discussed about power switching, power amplification in RF, and memory devices like flash, right. Of course, DRAM and SRAM, they are also devices with semiconductors, transistors. We are not talking about that right now, but you can just Google up and read. They are very easy to understand. What remains little bit is transistors in high speed digital logic, and after that we will go through some of the discussions on how to actually fabricate these devices practically. It is not a fabrication course, so we will not go into details. I will just give you a quick idea of how devices are fabricated in real world, right. What are the techniques and equipment used, and maybe in the last 2 or 3 lectures that are remaining, we can solve some practice numericals from maybe previous year's question papers and so on. Okay. So let us come to whiteboard and finish up what is pending of transistor applications. So the last application note that I had said we should discuss is about high speed digital logic, and frankly speaking, high speed digital logic is something for which all the MOSFETs that we have talked about in this course are used. So essentially we are talking about CMOS. CMOS stands for complementary MOSFET. So you have a PMOS and you have an NMOS, which means you have a P channel MOSFET and an N channel MOSFET, and you can use them to make this inverter sort of things, right. You use a PMOS and an NMOS to make this inverter or NOT gate, and you can make all these digital gates that you talk about like NAND, NOR, XOR and so on. These digital circuits or digital gates that you are learning or you have learned, these digital gates are made possible primarily because of this PMOS and NMOS. It is a very comfortable and best platform. It is called CMOS platform, and CMOS enables you to make these digital logic circuits which are high speed, that have enabled the processors, all these computers in mobile phones, right. And with gradual shrinking of the device dimension, which comes with Moore's law, you are able to make the devices faster and incorporate more functionalities in the chip. That is because you have more and more devices per unit area. That is what Moore's law says, that the number sort of doubles every 1.5 years. It has been going on, saturates going on, and people predict it will end, but we will see when it ends, right. So you are shrinking the transistor dimensions from microns to 180 nanometer to 90 nanometer, 65 nanometer and so on, right, 45 nanometer. Now we had also 22 nanometer. Now people are talking about 15 nanometer, which is commercialized, 7 nanometer node, where Samsung and TSMC are competing there. 7 nanometer node is also now almost going to be real. Of course, this 7 nanometer, now in this game, this is also business game. What these dimensions mean, initially they meant like maybe the size or the gate length or something of the transistor, but now essentially it means the distance between 2 DRAM lines, or the distance between 2 adjacent lines, the resolution in a way you can say 7 nanometer. But please remember that 7 nanometer for Intel and 7 nanometer for Samsung will not be the same. These companies have different terminologies nowadays. So for example, 7 nanometer of TSMC might be actually 10 nanometer of Intel and so on. This shrinking of these transistor dimensions allows you to get devices that are faster, and you can incorporate more functionalities because you have more number of devices per unit area. This is all primarily done for high speed digital logic. Okay. This is primarily all done for high speed digital logic. So all the digital circuits, NAND, NOR, all these gates are made of CMOS logic. So all the things that you have learned in MOSFET and MOS capacitor, they have essentially been contributing to this high speed digital logic. Okay. High speed digital logic can also be made of BJT sort of thing, by CMOS and all, but there is always this loss that is associated with BJT, because in a BJT, if you remember, you have emitter and then you have base and then collector. You have a base input current going in. So this base current essentially is a input current, and there is always a I square R loss. You will actually keep losing power because of this base, but in a MOSFET you have this insulating gate. No, this is N plus, this is N plus, and then there is an oxide here. On top of that you have the gate metal. So this oxide has very little current leakage. So your input loss side, the current leakage, current loss, offset loss will be very low. That is why people, and also the ease of fabrication and scalability is better here. You can have a large density of devices in CMOS, and that is why high speed digital logic has been preferred for CMOS. CMOS is preferred for that, and you want to make the device faster. So essentially the high speed digital logic consists of charging and discharging of capacitors. Okay, it's all about charging and discharging of capacitors. All these NOT gates, NAND gates, you see physically, in reality they are actually capacitors that you charge and discharge, and the charging time and discharging time of capacitors in this case actually is the capacitance value times the change in the voltage that you are doing divided by the current that is implementing the. So, you have a capacitor, for example, a node. This capacitor could be a transistor or something that you are actually discharging. What is the current that is used to charge and discharge, that is this. What is the delta V, the potential you are actually moving around, that is this, and C is the capacitance of this thing. So, to make devices faster, you need to make sure that your this time that is taken to switch to charge and discharge should be as low as possible to get a device that is faster. And for that you need a low capacitance, and you also need low voltages. You need low voltage drives, or you can say low voltage biases, right. So, that is why with faster generation, latest generation devices, your VDD is also shrinking. VDD is your the bias, and this bias is shrinking, so that you know the voltage that you have to move around across these devices also reduces. You can get faster devices. So, drain bias does play a role in the device, how fast they are working in a way. And with continuous shrinking of these devices, you probably have known this, and I probably have told this in other, you are shrinking the device dimensions both laterally and vertically. So, which means the gate length is reducing, but along with the gate length you also have to reduce the dielectric oxide thickness, because you need to maintain an aspect ratio. Your thickness of the dielectric, the gate dielectric also has to reduce. I told you about the constant field scaling, constant voltage scaling. All the device dimensions are shrunk in such a way, including doping. They need not be all done to maintain the constant field or constant voltage, but all the different dimension of a MOSFET, you know, this is N plus, and then you have a oxide here, and then you have a metal here, sort of thing, right. Then this is the doping. So, you know, this doping level, this depth of this junction, this doping of this junction, the junction depth, this length, the transistor length, this thickness, the gate oxide thickness, all these are reduced appropriately so as to ensure the device works close to what we want, the device works as desirable as we want. Okay. So, this shrinking has been going on. The gate oxide, for example, has been reduced, and with reduction in gate leakage, your leakage increases. So, that is why people have gone for high K dielectric, that I have already told you in one class. Using a high K dielectric, you can have a thicker dielectric, but the capacitance action is the same, right. So, then short channel effects come in all these scale devices, that also we have discussed in details. Short channel device effects come when a device has become very short, maybe 100 nanometer and less than a few hundred nanometer. Short channel effects can also kill your device, so you have to take into account there. There are things like strain channel, germanium silicon alloy strain channel, where you can enhance the mobility of holes, for example. You are talking about new types of metal contacts, polysilicon contacts, interconnect delays have to be reduced, because there will be multiple layers of these transistors that you have to connect from many lines. These are called interconnect lines. You know, from one transistor to another transistor you will have lines. These interconnect lines also will lead to parasitic resistances and capacitances. You have to reduce the interconnect delays. So, when you have multiple layers, you know, one layer would be your transistors, for example, then you have interconnect dielectric. So, that will be a dielectric layer that will separate, then there will be another metal line here, then there will be again another dielectric, some silicon nitride, another metal layer here. So, we keep doing this for multiple layers of integration, and this interlayer dielectric or interconnect dielectric can, you know, also increase a lot of delays and slow down the circuit. So, for high speed digital logic you need dielectrics with low dielectric constant in this interlayer dielectric, so that the charging discharging delay is smaller. Whereas, for gate oxide you need a high dielectric constant to make sure that you can have thicker oxide and still have lower leakage, and you know, equivalent oxide thickness is high. So, there are many of these things, and eventually everything has culminated in Moore's law, and all this Moore's law applies to the shrinking of the transistors, and all this shrinking of the transistors and everything that we do is primarily to do with high speed digital logic only. Okay, high speed digital logic. So, high speed digital logic, all the digital circuits we have learned that all it goes here, and now in more recent times, you know, CMOS is a planar device, and a planar device at such a small dimension as 15 nanometer, for example, or 22 nanometer, at such dimensions your CMOS planar device will have terrible short channel effect. Your gate is always at the top, right. So, you have an N plus, for example, N plus here, and then you have a dielectric here, it's silicon dioxide, for example, or whatever, hafnium oxide. it's a high K dielectric that you use. It cannot use silicon dioxide only. So you will use like a hafnium dioxide, and then you have like a metal here, right. What I was about to tell you is that, you know, it's a planar device, so you can think of it like a planar device sort of a thing, right. It's a planar device. It's a planar device. But in planar device, the metal will only be able to influence the gate from the top. So the channel depletion and other things are difficult to control because of short channel effects. So what people have come up with something is called tri-gate devices, tri-gate architectures, or these are also called FinFET because they have like a fin. Their device looks like a fin. These tri-gate actually architectures are such that the gate will not be only on the top, the gate will wrap around. The gate will wrap around the channel. The gate will wrap around the channel from 3 sides, not only one side, from 3 sides. Okay. So what it means is that you might have like a, you might like have a fin like this. Okay. Actually, I am not very good at drawing, but you might have a fin like this, and then this will be this will be like a source, and this will be like a drain, and this fin, this is like a connecting is silicon only. Your gate will like wrap around this whole thing, right, from the other side also. The gate will wrap around, all around, top, bottom, everything with a dielectrical force will be there, but it will wrap around everything. It's like you can think of, you know, this is the side view, but in the front view you can think of like this kind of a structure, right. So source is here, drain is there, for example, and the gate will come up, you know, on top of this like this, right. It will also go on the other side, of course. So it's like a FinFET or a tri-gate architecture that helps a better confinement of the carriers. A better channel control is coming because, you know, you have your gate that wraps around the channel and it gives you a better control and you know, control short channel effect, better control of threshold voltage, you know, current modulation and so on. So commercial devices in processors and all actually employ tri-gate FinFET architectures. The digital planar CMOS logic is used, but not in 15 and 20 nanometer nodes. If you have large devices like, you know, 180 nanometer, maybe a few microns, you still use CMOS there, but all these devices like 15 nanometer, 22 nanometer, people actually use FinFET and tri-gate architectures for your commercial devices. Okay. So this is basically about high speed digital logic. So that's pretty much about high speed digital logic. We have finished whatever we wanted to do it. Now what remains now is I will spend the rest of the time in this course that we have, maybe a few lectures more, partly in going through quickly about the practical aspects of fabrication that we will discuss right now. So we will go through the aspects of fabrication, the practical aspects of fabrication that we should be aware of, because it is not important that only we understand the devices and the physics of semiconductors, but we should be just basically be familiar with the real aspects of device fabrication, so that whenever we design a new device or we talk about device, you know, engineering, we should also know the limitations of the fabrication processes, because in reality you have to fabricate a device, right. So there are many of course devices, but I will talk about a classic MOSFET, for example, you know, how do you fabricate a MOSFET, and then of course if you know how to fabricate a MOSFET, then CMOS fabrication can be understood. We do not have to go in very details because this course is not a fabrication intensive course. So there are many key steps. Okay, there are many unit processes of fabrication. What I am telling you here are unit steps or unit processes of fabrication of semiconductor devices, and these unit processes of device fabrication are, you know, they are used in conjunction with one another, or they are used in a particular sequence, particular fashion to enable device fabrication such as a MOSFET. So for example, and this is not in sequence I am talking about, I am just talking about the unit processes that you use. Okay. So for example, one of the unit processes is oxidation. When I say oxidation, I typically mean say thermal oxidation. Okay. So this process is used to grow silicon dioxide gate dielectric, for example. Okay. For example, you need to grow silicon dioxide gate dielectric, right, that you remember, and there are other approaches to also growing or depositing silicon dioxide, but this gives you very high quality thermal oxidation, and this is primarily used for making the gate oxide, for example. I told you there are other also techniques to use silicon dioxide. Suppose you want to use silicon dioxide as an interlayer dielectric or some other, you know, layers sort of thing. Then you have two techniques, one is called diffusion and one is called ion implantation. These are techniques that are used, these two techniques that are used for doping, you know, p-type and n-type doping in semiconductor, and these are for silicon I am talking about, not for compound semiconductor. This diffusion and ion implantation are typically used for doping in silicon, all this doping of p plus n plus pockets and the channel and the p-type substrates and n-type substrates and so on, these are used there. Then of course you have deposition of different materials including metals, dielectric, insulators. This can be physical deposition, physical, like you are using a brute force, some kind of physical vapor deposition and so on. It can be also chemical deposition, where essentially you have a chemical reaction that will deposit the material. You can use this to deposit dielectrics including silicon dioxide, by the way, dielectrics. You can also deposit metals, you can deposit polysilicon, remember polysilicon gate you can use, and then you can put silicide and so on, many things can be deposited here. One of the important techniques, and of course all of these will need very intense equipment, very expensive equipments. These are housed in something called clean room. A clean room is where you have very controlled environment, minimal dust particles and so on. This needs very ion implanter, for example ion implantation needs ion implanter, which is a very expensive equipment, maybe in the order of 20-30 crores. It needs extensive effort in maintaining, also you need experts. So these are expensive tools that are housed inside clean room to in a way to enable the device fabrication. Deposition, for example, can be many types of deposition, and all these types of deposition, physical or chemical, are very expensive tools that are that are only in the select areas. For example, this is a clean room. Then there is this approach or technique called photolithography, and this is the most basic and most crucial. Photolithography is essentially transferring the pattern. You have this source, drain, gate. I am talking about the top view, okay, source, drain, and the gate finger will come like that, right. This is gate, for example, this is a device isolation. You need to transfer this pattern to the silicon substrate from the mask where you are writing. You have like a mask, it is a chrome glass, for example. On that you have these small features, you cannot see with eye, probably they are microscopic or nanoscopic features. These are like transistors, maybe there is a source, there is a gate, whatever, and then you have this silicon wafer below, the silicon wafer below sits below. On the silicon wafer you have to transfer the mask patterns, so that you have all this source, drain, all these source, drain devices here, maybe source, drain, source, drain, source, drain, all these devices are there. You have to transfer these patterns from from the mask to the actual wafer by exposing them to UV light. There's so many things, okay. This process is called photolithography. You can think of it like a old time camera, if you see that reel, you have an old time camera, you take the click the picture, this Yashica and all these Kodak cameras, similar thing, but at a much smaller scale, nanometer scale or so. You can transfer the pattern from one to another, okay. And the final is called etching. Etching is basically removing, you are removing material from a wafer. For example, you might have a silicon wafer, I am not drawing it nicely. For example, you want to, if I draw a cross section view, maybe you have this n plus pocket, and then you have a gate oxide, then you have gate here, this is source, this is drain, but you want to isolate it from another device. So there is another n plus here. The reason you isolate is that you do not want one device to talk to another device, affect the other device, so you isolate. So these strands that you have created, this strands that you have created, this isolation, this is etching. You have etched the silicon away between two. So etching also, in a way, you can design some funky structures. You have a silicon wafer like that, you want to have different structures that are, you are etching the silicon away in some areas, you are etching the silicon away. You can have different sort of structures, V shape, or you can define the depth or whatever. You are removing the material from selected portion in a selected fashion and trend. This is called etching. So oxidation, thermal oxidation, diffusion, ion implantation, deposition, photolithography, etching. These are steps, and each of them have many, each of them has many subgroups, categories, like deposition has LPCVD, PCVD, MOCVD, so many things, right. So they have all these things together, these are unit steps of fabrication, and you use these steps to make devices, and this is particularly in the context of silicon devices that I am talking about. So we will quickly run through all of this very briefly as to what each is all about, without spending so much time, right. We should just be aware. So first one is oxidation, right. The first one is oxidation, and I mean thermal oxidation. We will not go through the maths of anything. Thermal oxidation essentially is that you take the silicon to high temperature and you oxidize it to get silicon dioxide. So, any piece of silicon will always have like a small native layer of oxide here on the top, but you take it to high temperature, you heat it up, and then you flow some oxygen or water vapor, some gas to oxidize it, and then you will have a layer of silicon dioxide on the top. This layer of silicon dioxide does not come magically. This silicon actually oxidizes. Some top part of the silicon will oxidize and it will give you like a silicon dioxide layer. It will give you some silicon dioxide layer. So, that silicon dioxide layer actually forms because the silicon some part is oxidized. So, it will eat away into some silicon, okay, it will eat away into some silicon because it is oxidized from silicon, it will eat away some silicon. Typically, you flow pure dry oxygen vapor, oxygen gas, or you flow pure dry, pure not dry, pure water vapor. One is, this is called dry oxidation, this is called wet oxidation, and typically the temperature that you heat up the whole thing is depends, but it is typically from 900 degree to 1200 degree Celsius, which is fairly high, and the gas flow, this oxygen or water vapor that you flow typically is in the rate of 1 liter per minute. Okay. So, you have like a chamber like this, you will have an outlet here, and then you have a gas like this. You have this different sort of thing, you can put oxygen, maybe you can purge some other gas, you can put water vapor or whatever, and then there will be a platform here where you will keep the silicon wafers like that vertically, for example, okay, and then there will be heater, this coils will be there, heating coils will be there, that are like inductive coils or whatever you can say, and then there is an exhaust here, okay. So, you heat the whole thing and you flow these things. You typically use it to oxidize it to make gate oxide and also something called field oxide. Field oxide is the oxide that is used to separate one device from another device. So, these are typically used there, and the classic reaction is essentially silicon reacts with oxygen at a temperature of more than 800 degree Celsius, maybe 900, to give silicon dioxide, that is the dry, and in water vapor, if silicon acts with water vapor, it will give you silicon dioxide plus a remnant of hydrogen gas, right. As I told you, silicon dioxide interface will now move to the bottom, okay, because some portion of silicon has been eaten up. So, the silicon interface will move to into the silicon during oxidation. To grow 100 nanometer of silicon dioxide, you will have to consume 44 nanometer of silicon. That means, if you want to grow 100 nanometer of silicon dioxide on top of that, then 44 nanometer of silicon will be consumed, will be oxidized if you do a mole fraction analysis, and then you will get a total of 100 nanometer of silicon dioxide, okay, that is the funda. And this oxidation process has a lot of mathematics involved, like you want to find out the rate of oxidation, there is this Fick's law, how much surface you need in a concentration and all these things, which you will skip carefully. So, you for thicker oxide, typically if you want to grow field oxides and all, you use wet oxidation, and if you want to grow the gate dielectric for thinner oxide, you typically use a dry oxidation, right. Now, then next we come to doping, right, and first in doping we will use diffusion. So, diffusion you have learned, diffusion is of gas particles at one place will move to another place and all these things, but here I am talking about diffusion to dope the substrate. So, what you do is that you have something like this is a silicon wafer, for example, you have to make some hard mask, like you have to make some silicon dioxide or some mask you have to make. This is a hard mask that you have to use, okay. It can be say maybe silicon dioxide or something, and then you expose this to doping, expose this to diffusion, like you will flow some gas, phosphine, arsine or whatever, and then you will see that it will fall on the surface, it will react, it will diffuse, it will diffuse inside the surface like this. It will lateral, because diffusion is isotropic, it will go in all things. So, this is the depth, there is a depth to which you are diffusing, there is a concentration gradient here, many things are there, but that gas will flow and it will diffuse wherever it is exposed to the gas, wherever it is hard mask it will not diffuse, it will diffuse laterally there, right. So, this is about diffusion, you are doping. So, this is like a pocket of doping, you can say N plus or P plus whatever. So, what you do is that you place the wafer in a high temperature, you place the wafer in a high temperature quartz tube, same thing as like a thermal oxidation. You place the wafer in a high temperature quartz tube, and then you pass the dopant gas. You pass the dopant gas at high temperature. For example, the temperature can vary again between 800 to 1200 degrees C for silicon, and then the number of dopant will depend on the partial pressure of the dopant impurity gas that you are flowing, the partial pressure of the dopant impurity gas that you are flowing. Typically, you will use boron for p type and arsenic or phosphorus for n type doping. So you can have dopant sources. Dopant sources can be solid state sources or liquid sources or gaseous sources, like you can use boron nitride as a solid source dopant, you can use BBr3 boron triboroid as a liquid source, or you can use arsine for example as a gas source. There can be liquid, gas, solid source, many source of doping, but you have to flow the dopant vapor and in a very high temperature so that it will diffuse in a way. Okay. And it will, for example, you might take an example of phosphorus, maybe trichloride, that if you put it in the oxygen environment and you pass it, you will eventually get pentoxide plus chlorine, and then this pentoxide that you form, it will form a glass on the silicon wafer, and that it is subjected to reduction to reduce phosphorus. So you have to subject it to this heated silicon. In that case, it will form phosphorus plus silicon dioxide. So this phosphorus will be formed on the surface, for example, right. So this phosphorus will be released in this surface here, as talking about this phosphorus is released there, and it diffuses in the silicon. It diffuses in the silicon. That's what happens. Okay. There can be two types of diffusion that you do, very briefly speaking. One is called constant surface diffusion, which means you maintain a constant surface concentration diffusion, which means you maintain a constant concentration of the dopant at the surface of the wafer and let it diffuse below the surface. Okay. So the total volume might change of the dopant throughout the surface, throughout the wafer. And one is called constant total dopant diffusion. What it means is that the total volume of doping that you are using is constant. At the surface you may not maintain a constant gradient. So what I mean is that in constant surface concentration, if this is the depth of the silicon wafer where you are diffusing, then on the surface you will have constant diffusion. So at different diffusion coefficients or corresponding to different temperatures, you will have something like that at different temperatures. At the surface you will remain constant, but over the depth, the volume of the doping might also change. In constant total volume, you ensure that the total volume or constant total dopant in the total dopant you are using is constant. So for example, at one temperature you have a profile like this is depth, of course. At higher temperature maybe it will diffuse more like this, even higher temperature will more like this. So the area will remain constant under is, at the surface the concentration will reduce, it will go deeper, okay. But in constant surface it will be like this. So there are two types of diffusion, both are used in silicon processes to dope. Typically two-step processes are used. A pre-deposition diffusion is used where you use a constant surface, and then you use a drive-in diffusion at little higher temperature, maybe you basically do a constant total diffusion, okay. That's what you use. And in diffusion, of course, even if you have like a hard mask, this is a hard mask for example, and your diffusion is coming, there is diffusion gas, the diffusion will actually be lateral, it will actually go like this because it is a isotropic sort of thing. So there is also a significant lateral spread in the diffusion. There is a lateral spread of the diffused doping species, and also it is sort of isotropic. So it is not, it's basically it spreads everywhere in the wafer, in all the directions it can go. It is not like an anisotropic diffusion. So that is why people have nowadays also resorted to ion implantation, which is the next topic. People use still diffuse diffusion, please do not get me wrong, because they can do much depth, higher depth they can go. And then you have ion implantation. What ion implantation does is that you have a high energy beam of ions. So for example, this is your silicon wafer. Here you do not have to use a hard mask. This is a room temperature process only, you do not have to heat it up, unlike diffusion. So it is a low temperature process. You can have photoresists, I will come to that photoresists later. Photoresists are like organic compounds that will protect the surface at certain areas. These are easy to put, room temperature process, and you use a high energetic beam of say phosphorus, whatever, or arsenic or boron, so that the doping is actually isotropic. So the doping will only take place here, anisotropic, okay. So the doping will be actually only in this, and the depth to which you go of the doping can be decided by the dose, the energy of the doping, these items that you are giving. It is a very expensive tool called ion implanter. It is a very high energy beam of ions that are bombarded, and then they go and form this kind of a pocket. It is anisotropic, there is no lateral diffusion here, it is very controlled, but it can do it cannot do much higher depth. Also you will have some crystal damage because it is very high energetic process. It is a very high energetic process. So one is that you can do it at low temperature, you do not need to go to high temperature process. You can use a photoresist mask, which means it is a very simple process that way. It gives you anisotropic doping profile. So, it is ekdam pocket like a vertical wall sort of, you do not have diffusion here. It can be, you can control the depth of the junction and the concentration independently. The concentration and depth of the doping can be independently controlled, unlike in diffusion where the concentration and depth are related. It can be done here. You can do batch as well as single wafer. You can do batch by batch, or you can do single wafer process, right. So, that is an advantage, because in your diffusion you will need high temperature hard mask and isotropic doping profile and so on and so forth, right. It is a very expensive tool. Ion implantation, as I told you, you have an ion source in some way, you have an ion source that that generates the ions, but then you have a magnet sort of thing, so that only selected ions with specific mass ratio E by m can actually get deflected. They go through a lot of accelerating plates, so that they get accelerated at high voltage. You have many filters and beam focus and other things, and eventually you have the wafer, the silicon wafer, where you can scan them X and Y, so as to dope. If you have a wafer like this, then you can essentially scan and make sure the doping is, you can control the doping in different parts of the wafer. But the disadvantage is that it is a high energy beam of ions that come, so there is some crystal damage. And all the beams of ions that have fallen on here will essentially make sure that phosphorus or boron, whatever you are doing, they will all go and sit in the lattice side, they might not get ionized. So, you have to do, after the ion implantation is done, you have to do a high temperature anneal. You have to do a high temperature anneal to recover the crystal loss, and to make sure that all these dopant atoms that you have added like phosphorus or boron, they are activated, they are able to donate or accept electrons now. You need to activate them, okay. You need to activate them. It is also a very costly tool, very high maintenance also is done. So, most of the academic institutes do not have an ion implanter, right. And in ion implantation, of course, initially when you implant it, it will not abruptly stop like that. As a function of depth, the doping profile will look something like this. So, there is a Gaussian distribution, there is a range to which you go, there is a straddle, the deviation, but anyways, with annealing you can actually approximate like a you can approximate as a uniform profile. Here you can get the depth and doping profile. It is very important, okay. So, that is an important aspect of ion implantation. You can do all the simulation tools that are used to predict how much dose of ions you need, what is the energy of the ion, the angle, the tilt, the rotation of the wafer, and so many things are there to ensure that ion implantation is done to get this very high aspect ratio, or this highly anisotropic profiles can be obtained in a doping sort of things, okay. So, that brings us to an end to this lecture. We have finished up some of the parts of fabrication now. We are still a couple of lectures remaining to finish the course, and today's class will end with this discussion on ion implantation. So, we have taken care of, we have started this lecture with the remaining of the CMOS high speed digital logic. We have introduced many of the fabrication techniques, what are the techniques that are needed, like photolithography, ion implantation, diffusion, and deposition and so on. So, these are the things that we will study. We have covered thermal oxidation, we have covered diffusion and ion implantation, which are used for doping, right. And in the next class we will probably go through some of the deposition techniques, how do you deposit metals, dielectrics, and different kinds of polysilicon and so on and so forth, physical and chemical depositions, and then we will go through etching and photolithography, so that we are familiar with the very basics of how device fabrication is actually done, okay. So, thank you for your time, and I will see you in the next class.